Yeah, good morning, everybody. I would like to present my project. But first of all, I want to mention about the name of the project. The name is really unique because we're going to use non-line of sight signal to solve one of the most challenge face millimeter wave and terahertz. There is no doubt that on next generation and beyond, we will need the huge and massive bandwidth supported by millimeter wave and terahertz. This is due to the need for the new use cases and applications, especially for open RAN, open radio system. To keep using the conventional frequency band was limited with the bandwidth that's can't support what we need for future, for next generation. That's why there is a really strong need for expanding the frequency for millimeter wave and terahertz. But there is no secret. The challenge comes with the use of the millimeter wave and terahertz, which are really sensitive to the blockage, and even weather can affect the millimeter wave and terahertz. That's why for 7 years I'm trying to focus on finding some solution can help we can use that frequency, that's a huge band in future networks, 6G and beyond. The name of our project is Continuous Steering Backup of Non-Line of Sight. As you know, like in the conventional system, they try to avoid no line of sight or immediate as much as, because it's kind of a noise, can affect on the noise. But my opinion is why we don't use it instead of we avoid it, because in some case when blockage happen or obstacles, no line of sight signals might be more than line of sight. So in here we are continuous steering backup of non-lines to assist millimeter wave to avoid the blockage. This is the main topic. I'm gonna show you in here an example of the real world scenario. Let's assume here we have a BTS, millimeter wave BTS, and in a normal city, anywhere, and we have a normal crowded street with a lot of cars, different bus, truck, whatever. And our target is this red car. Our target, we want to reach the signal, is this red car. But this red car is totally broken by this van. I don't put a bus or truck because I'm gonna take most of the pictures. I just mention about a small example which is real in the real world. And here the signal comes and it's just signal is blocked by these obstacles. So this is a really real world case, real world problem that affected to use millimeter wave and terahertz, which is really needed. So I'm thinking, okay, this is a main signal, this is a line of sight, and here we can see the ground reflect or surface reflect or obstacle reflect signal, which is even more than the line of sight. 1, 2, 3, 4, I don't know, whatever. Here, it might be a solution. A solution might come in here. Where is in the city a lot of smooth surface, like a building now, a new building just made by glasses or smooth surface that is really good for reflecting the signal. So in this case, why we don't use the reflected signal as a backup in the same area? We don't, not everywhere, because there's another building like harsh, the body of the surface of the building is harsh, but in some cases, when we surrounding the environment by a smooth building, they already designed it. Why we don't program the BTS? They can reflect the signal in here and then like attack the target. I'm gonna show you a small video from where this idea comes from, because every time when we have a problem, we can find a solution in the real world. For example, now everybody knows this game. This is a billiard game. So when we, for example, this is the BTS, the white ball is the BTS, and the blue ball is our target. And here, the yellow one is just an obstacle. So this is the real world game. So when the player, he wants to reach imagine this is the line, imagine that's the line, it just show the wave, the beam of the millimeter wave of her. So look at her. So look at her. I'm just mentioning it, totally blocked, Look, her is totally blocked. The line is coming, but it's blocked by this one. Blocked by the yellow ball, which is obstacle. And we are targeting here. So what are we gonna do in here? The player, he has to find another angle that he can, inside the signal, he tries to find another angle that inside the signal and can hit the target. So they're gonna find the, okay, I'm just gonna back in, I'm just gonna back in. Okay, so look, when you move the signal, when he tried to find a signal here, okay, he should back, okay, this is the right one, they're gonna back again to estimate the signal, or another one. We have a two signal, we have a two-way to attack the target. We have a two-way. We can use this way, this is one, I'm gonna show you again. We have a two-way to attack the target based on the environment. Here's the one, we can do it, and another one in another side here. So just hit the ball, at top, we got a target. So this is what we're gonna do. We just avoid the obstacles by finding another obstacle. Another example in here, example to show, this is totally blocked, totally blocked the line. Our target is this ball, number 4, and this is an obstacle, number 2. And look, totally blocked. So what we're gonna do, we're gonna try to find another angle, not a straight, not a line of sight, just a backup to hit the target and reach. And this is what we're gonna do. We can estimate around this surrounding where we can hit the ball. So the player gonna choose maybe this target or this target, and he tried to estimate. We can use this as a code book. We can use a code book for a beamforming to find her. Estimate. Okay, this is my signal, the angle. So hit the ball. Okay, we reach the target by avoiding the obstacle. So here is a picture of the reflected, the angle of reflected signal on a smooth way. Here is the spectrum reflected on a smooth surface. So you can change the inside angle, then you can find a different target angle. As you change the incident angle, you can find another reflected angle. Okay, I'm gonna back to my presentation. So here's an example on the real world. BTS surrounding environment by different building. We gonna choose where we put the BTS. We don't put it randomly, just in a specific place there where is already the building can reflect the signal well, like smooth. And just 1, 2, 3. And this line will keep as a backup. Even we support by line of sight, keep a line of sight, but we will keep a backup. This backup keep continuing. In case the line of sight is disconnected, at least the non-line of sight can keep the connect with the BTS till the BTS for a synchronization, for the just synchronization or timing till the line of sight back. We know we just try to avoid the blockage, because blockage or outage meaning the BTS has to start again as a new BTS, even is connected, and after a while, like when outage happen, then the BTS have to start again, like a new user, like use the extensive scanning to find the best beam pair, and like which is really overhead, which really causes a high overhead. So here's an equation, like equation of we're gonna use two kind of a beam, which is the line of sight beam, and here we have a backup beam together at the same time. One direct and another reflected in different angle. One in the straight angle, another in a different angle. That's a backup. Anytime the line of sight get down, the backup can keep support the device by the time and synchronization and even a little data till the main line of sight come back. So in this case, we have two-channel model. Here is a two-channel model. The first channel model, which is a line of sight, and another channel model is just a backup non-line of sight. They are simultaneously support the target during the connection. And this is the equation. I know when I'm like give you a headache with a lot of math equation that's support the line of sight and no line of sight. But this is another example to show you more details. This is another example to show you more details on how our system is working. Here's a BTS, millimeter wave BTS. The line of sight, when emitted from the BTS, it could be have a line of sight path, which is strong, direct to the target. Another one is just hit the ground and make another reflected. And other one, what we want here is turning back up, which is stacking here and coming here and looking here. We have the huge of the beam surrounding by the target, which is really useful. Really useful. In this side, if this side block, this side can support. If this side block, this side. So we can surround our target by beams, which is make it high probability. We don't go to the outage stage, which is really hard. We try to avoid it. Here's a simulation. I'm gonna go to the simulation parts. And here we just measure the vehicle density versus the outage probability. You can see on the conventional system, to go in the outage is more high than our system. And here we estimate the blockage duration versus the CDF. We will see really huge and different gaps between both systems, because our system duration blockage is really less than conventional system. Okay, this is my presentation, and if you have any questions, please go ahead.
Thank you for good idea and thank you for excellent presentation. Do you have any questions or comment? I think.
Thank you for the presentation. My question is, what level of accuracy that requires for the target angles, like the target object is blocked by some other obstacles, and you choose some path to reach the target target object line. So what kind of angle accuracy is required when you use reflection
Yeah.
and you like you need to make an angle.
Right. Right.
So what's the level of accuracy required to reach the target?
This is gonna calculate it in advance by using a program because the building place is fixed. BTS is fixed. There is no change on the position of the BTS and the building. That's it. Two angles are fixed. And the way of the car is just like we can estimate it, not a big random, just them. So mostly the ground will be on the between 5 meters. There's a 5 meters that we have to estimate. So when we made the signal on the surface, we estimated that we're gonna down. So that's gonna be built as a code book. Code book for a beamforming, we're gonna estimate everything based on our BTS position, building, and because this building and next building, the body structures are different. Maybe one building is glass, another building is concrete. So we're gonna estimate this. First building, if we incident our beam on this building, then we have to estimate based on the materials that the building built by, glass or a concrete or even iron or whatever. So we're gonna estimate. Then when we when we reach another building, the estimation gonna different based on the. So that's algorithm gonna be in advance based on the location and the distance and even the height of the building. Yeah, so this is not a complicated at all because it's just so we can estimate the inside incident angle and reflected angle based on the location. As I told you, we have already two fixed locations, BTS and a building. So this makes it really easy to just, as I showed you in the video in the billiard room, the main ball is a fix, and the surrounding the edges are fixed. So easy to estimate the angle based on a way up. One more thing. In here, we're gonna use a camera. The BTS, this is supported by the camera. I don't go into the details because it takes a really long time. So this BTS supported by the video camera. Video camera that can estimate the location of the target. So to estimate the location of the target exactly, this BTS is supported by the camera, video camera that can use the video image to find the location of the target.
Thank you for the explanation.
Okay, and in my private opinion, there are good ideas, and I think there are a lot of considering points, like some test rules, like some pen installation rules, the reflection, deflection. There are a lot of the scaling points.
Yeah.
In the future, I think could you considering there are a lot of environment in the proper system.
Yeah.
Okay. And second, the thinking. I think you already know the RIS, reflection intelligent surface. I think your corporate system is very the good idea, nice idea, the excellent idea. And in the future, could you the concept of the RIS, reflection intelligent surface to your corporate system?
Yeah.
Very the combining points.
Right, we can put the service on somewhere on the building, that we can use it. But for now, I just try to use a little high power, then we less cost. I want to reduce the cost. I want to reduce the cost as much as I can. We can use some building is good reflected, like a lot of building nowadays made it by glasses, and the glasses with a color is just a mirror for reflecting. So we can get I'm telling you, we can't support the data, like a huge data, but at least we avoid outage. And this is very important to avoid the overhead, because to BTS go in outage and re-establish the link again, like the conventional system have to extensive scan and scan all the beams pairs, and this is really huge overhead, time delay and power, and so this is just one of the solutions that we work for in 6G and beyond. We have another system we develop now, is called HRAM, which is gonna publish soon on a journal, is really can help to revolution in conventional system.
Okay, thanks again for your good presentation. Okay. And then can I move to the next presenter and the fifth presenter? Are you ready? Number 4, 5, okay. That's it. Could you start, please?
Chair, for my introduction, I'm a professor from Taiwan Institute of Technology in Japan. Today, I'd like to present evaluation of effect of congestion on time synchronization accuracy in IEEE 802.1 AS. First, we explain the background of this research. With development of autonomous driving, the number of electric control units in automobiles is increasing, requiring